Welcome back students. I am Dr. Rajesh Singh and in this video we will continue solving exercise 4.3 from the book Bartle and Sherbert. In the last video I solved question number 1 to question number 4. In this video I will solve question number 5 onwards. So let us start with question number 5. Solution. So in the question number 5 we have to evaluate the following limits, or we have to show that they do not exist. So let us start with a part. So here I will show that, because if I will take limit x tends to 1, so this will go to 1 and this will go to 0 from the right side, so it will go to plus infinity. So I will show that limit x tends to 1 positive x upon x minus 1 is equal to infinity. So this is what I have to show. So I will take let k greater than 0. This is I have to show. So let k greater than 0 be any real number. Then what I will do, I will take to show there exists delta greater than 0 such that 0 less than x minus 1 less than delta should imply x upon x minus 1 greater than k. So this is what I want. So I will start with consider for x greater than 1 x upon x minus 1 greater than k. So this is equivalent to writing x minus 1 upon x is less than 1 by k, and then if I will add, if I will subtract 1 to both sides, then what I will get? So subtracting, so this is equivalent to writing x minus 1 upon x minus 1 is less than 1 by k minus 1. So this is equivalent to writing, I will get minus 1 by x is less than 1 minus k by k. So this is what I have got. So first let us multiply both sides by a minus sign. So this makes this 1 by x greater than k minus 1 by k. Now take the reciprocal. So I get x less than k upon k minus 1. Now this is greater than 1, so the k minus 1 is greater than 0, so k is also greater than 1. So which is equivalent to writing, so I can write it like this: x minus 1 is less than, if I will take minus, then I will get 1 by k minus 1. So I have subtracted minus 1 from both sides, so this, and k is greater than 1, because what I am getting, this x is greater than 1. Since x is greater than 1, so k should be greater than 1, otherwise this will not hold. So this is there. So now I can take, so take delta equal to 1 by k minus 1 where k is greater than 1. Then 0 less than x minus 1 less than delta implies x upon x minus 1 is greater than k. Hence, by definition of one-sided limit, limit x tends to 1 positive x upon x minus 1 is equal to plus infinity. So what we take k to be greater than 1 be any real number. So make it k greater than 1 be any real number. So this proves part A. Now in the part B, because when I will take limit x tends to 1 positive, then it is same as part A, so it will go to infinity. If I will take x tends to 1 negative, then it will go to minus infinity. So we have already shown in part A that limit x tends to 1 positive, x upon x minus 1 is equal to infinity. Now we claim that limit x tends to 1 negative, x upon x minus 1 is equal to minus infinity. So for this we will take, let k greater than, again I will take 1, be any real number. So instead of 0 I am taking greater than 1, and because k generally represents large number, so I can take this to be greater than any real number, and still the definition will be true. So I am taking k to be greater than 1, be any real number. Then I have to show there exists delta greater than 0 such that 0 less than 1 minus x less than delta should imply x upon x minus 1 less than minus k. So this is what I have to show. So for this I will consider for any x less than 1. So I am taking for any x less than 1, x upon x minus 1 less than minus k. So this is equivalent to writing, so taking the reciprocal we get x minus 1 upon x is greater than minus 1 by k. So now taking the equivalence, this is equivalent to, I am subtracting minus 1 from both sides, so I get this is greater than minus 1 by k minus 1. So which is, on simplifying, what we get minus 1 by x is greater than minus 1 plus k upon k. So this is what we get. So taking the reciprocal again, so we get minus x is less than minus k upon k plus 1. So adding 1 to both sides, we get 1 minus x is less than 1 minus k upon k plus 1. So this is equal to, if I will take k plus 1, so I get 1 by k plus 1. So take delta equal to 1 by k plus 1. Then obviously 0 less than 1 minus x less than delta implies 1 minus x is less than 1 upon k plus 1, and this implies x upon x minus 1 is less than minus k. Thus by definition of one-sided limit, one-sided infinite limit, x tends to 1 negative, x upon x minus 1 is equal to minus infinity. So since limit x tends to 1 positive, x upon x minus 1 is equal to plus infinity, and limit x tends to 1 negative, x upon x minus 1 is equal to minus infinity. So limit x tends to 1, x upon x minus 1 does not exist. So this does not exist because RHL is not equal to LHL, so this does not exist. So now let me take the third part. What is the third part? So in third part we have to show that limit x tends to 0 positive, x plus 2 by root x is, to C part to show. So what we will show, limit x tends to 0 positive, x plus 2 by root x. So where this will go, this will go to, so this will go to 2 and this will go to 0. So 2 by 0 is plus infinity, where x is given to be greater than 0. So this we have to show. So to show that limit x tends to 0 positive, x plus 2 by root x equal to plus infinity, we will use the comparison test. So what was the comparison test? This was the comparison test. If fx is less than equal to gx and limit x tends to c, f is equal to infinity, then limit x tends to c, g is also equal to infinity. So we will take this equal to g and we will find some f such that the limit of f is equal to infinity at 0 positive. So this is the result we are going to use. This is comparison test. So this is written for both sided limits, but it is true also true for one sided limits. So we will use the comparison test to prove this. So let gx is equal to x plus 2 by root x or x greater than 0, and fx we will take equal to 2 by 2 by root x, or you can take it as 1 by root x or x greater than 0. Then obviously for all fx is less than equal to gx for all x greater than 0. So we just need to show, to using comparison test to prove limit x tends to 0 positive gx equal to plus infinity, we just need to show limit x tends to 0 positive 1 by root x is equal to plus infinity. So this is what we are going to show, and this will prove our result. So let us start. So let k greater than 0 be any real number to show there exists delta greater than 0 such that 0 less than x minus 0 less than delta should imply 1 by root x greater than k. So what delta we should take? We should take delta equal to, so consider for any x greater than 0, 1 by root x greater than k is equivalent to root x less than 1 by k, and which is equivalent to x square less than 1 by k square. So sorry, x less than 1 by, so which is equivalent to x less than 1 by k square. So what I will do, I will take delta, let delta equal to 1 by k square, which is greater than 0. So then for 0 less than x minus 0 less than delta, 1 by root x is greater than k, hence limit x tends to 0 positive 1 by root x is plus infinity, and thus limit x tends to 0 positive x plus 2 by root x is equal to plus infinity using comparison test. So this proves part C of question number 5. Now let us move to part D. So what is part D? So this is part D. So we have to show that limit x tends to infinity, x plus 2 by root x, and x is greater than 0. So to show limit x tends to infinity, x plus 2 by root x is equal to plus infinity. So this is what we will show. So what we will do, we will again use the comparison test. So same comparison test we will use. So we will take let gx equal to x plus 2 by root x. Now I want some function, because x is approaching infinity, so I can take x to be greater than 1, and then I can add a function which is easy. So x greater than 1 for all x greater than 1. So I am taking my domain to be greater than 1. Now let fx equal to x for all x greater than 1. So gx is x plus 2 by root x, and since x is greater than 1, so root x is greater than 1. So if I will replace root x by 1, I will get this x plus 2, which is greater than x, which is equal to fx. So fx is less than equal to gx for all x greater than 1. Now since limit x tends to infinity, fx is equal to plus infinity. So by comparison test, limit x tends to infinity, gx is also infinity. That is, limit x tends to infinity, x plus 2 by root x is infinity. So this completes part D of question number 5. Now let us see what is question number E. So in E part we will show that limit x tends to 0, root x plus 1 by x, this does not exist. So claim 1, we will show limit x tends to 0 positive, root x plus 1 by x is equal to plus infinity. So again we will take this as infinity. So again we will use comparison test. So for that, let gx is equal to root x plus 1 by x for all x greater than 0, and then so gx can be written as root x plus 1 by x. Now since x is greater than 0, if I will replace the x by 0 in the numerator, then number will decrease. So this is 1 by x. So let fx equal to 1 by x for all x greater than 0. Then obviously fx is less than equal to gx for all x greater than 0, and limit x tends to 0 positive, fx is equal to plus infinity. So by comparison test, limit x tends to 0 positive, gx is also plus infinity. Now claim 2, limit x tends to 0 negative, root x plus 1 by x is equal to minus infinity. So this is what we will show, that this approaches to minus infinity. So for this we will use the comparison test. Let gx equal to root x plus 1 upon x, and where minus 1 is less than x less than 0. So this I am taking. So for this I will define fx. So then gx is equal to root x plus 1 upon x. So since x is less than 0, so if I will increase my denominator, so this will be less than, if I will replace x by 0, then I will get this is equal to 1 by x. So again, let fx equal to 1 by x for all x belonging to minus 1 to 0. Then fx gx is less than equal to fx for all x belonging to minus 1 to 0, and limit x tends to 0 negative, fx is equal to minus infinity. So by comparison test, limit x tends to 0 negative, gx is equal to minus infinity. That is, limit x tends to 0 negative, root x plus 1 by x is equal to minus infinity. Thus we have shown that limit x tends to 0 positive, root x plus 1 by x is equal to plus infinity, and limit x tends to 0 negative root x plus 1 upon x is equal to minus infinity. Hence, limit x tends to 0 root x plus 1 by x does not exist. So this completes question number of E part of question number 5. Now we have to we will show we will start with the F part. So in this we will show that limit x tends to infinity root x plus 1 by x is equal to 0. This we will show. So to show limit x tends to infinity root x plus 1 upon x equal to 0, we will use quiz theorem. We will use Squeeze theorem. So for that, what we will take, so since x is approaching infinity, so we can assume that x is greater than 1. So define let gx equal to root x plus 1 upon x for all x greater than 1. Now consider for x greater than 1, obviously because x this is positive, so 0 is less than equal to gx, and gx is equal to root x plus 1 by x, which is less than, so since 1 is less than x, so I am replacing 1 by 1, so this is equal to root 2 by, or I can take it as root 2 by x, so this is less than 2 by root x. So I will take hx equal to, so let fx equal to 0 for all x greater than 1 and hx equal to 2 by root x for all x greater than 1. Then limit then fx is less than equal to gx is less than equal to hx for all x greater than 1, and limit x tends to 0 x tends to infinity fx is 0, which is equal to limit x tends to infinity hx. So thus by Squeeze theorem, limit x tends to infinity gx is equal to 0, that is limit x tends to infinity root x plus 1 by x is equal to 0. So this completes F part of question number 5. Now let us consider G part. So in G part we will show that limit x tends to infinity root x minus 5 upon root x plus 3 is equal to 1. So this we will show that limit x tends to infinity root x minus 5 upon root x plus 3 is equal to 1. So let epsilon greater than 0 be any real number. So to show there exists k greater than 0 such that x greater than k implies root x minus 5 upon root x plus 3 minus 1 is less than epsilon. So this is what I have to show. So consider root x minus 5 upon root x plus 3 minus 1. So on simplifying what we get, so which is equal to root x minus 5 upon root x, or minus root x minus 3 upon root x plus 3. So on simplifying what we get, 8 upon root x plus 3, and I want this to be less than epsilon. So this is less than epsilon if and only if root x plus 3 by 8 is greater than 1 by epsilon. So I have taken the reciprocal, and this is equivalent to proving that root x is greater than 8 by epsilon minus 3. So I will take, let k equal to 64 by epsilon square, which is greater than 0. So then x greater than k implies x is greater than 64 by epsilon square, and this implies root x is greater than 8 by epsilon and that implies root x is greater than 8 by epsilon minus 3, and this is equivalent to 8 by root x plus 3 less than epsilon, and which is equivalent to root x minus 5 upon root x plus 3 minus 1 is less than epsilon. So hence we have shown existence of k greater than 0 such that x greater than k implies root x minus 5 upon root x plus 3 minus 1 is less than epsilon. Thus, limit x tends to infinity, root x minus 5 upon root x plus 3 is equal to 1. So now we are left with the last part of question number 5, which is h part. So in this we will show limit x tends to infinity, root x minus x upon root x plus x is equal to minus 1. So let epsilon greater than 0 be any real number. Now what we will do, we have to find some k greater than 0 such that x greater than k should imply root x minus x upon root x plus x plus 1 to be less than epsilon. So this is what we want. So we will start consider for any x greater than 0. So we are starting with this. Root x plus 1, which is equal to, so when we will simplify, what we get, root x minus x plus root x plus x upon root x plus x. So this is equal to 2 root x by root x plus x, and this is equal to 2 1 plus root x, and I want this to be less than epsilon. So this is less than epsilon if and only if 1 plus root x by 2 is greater than 1 by epsilon which is equivalent to root x is greater than 2 by epsilon minus 1. Now, so what k we should take? We should take k equal to 4 by epsilon square. Ignore this negative number because this will create problem if I will take k equal to 2 by epsilon minus 1 whole square or something like that. So that will create problem. So ignore this negative now. It will be taken care like in the previous example. So k, so this k I have taken, then x greater than k implies x is greater than 4 upon epsilon square, and this implies root x is greater than 2 by epsilon. So this implies root x is greater than 2 by epsilon minus 1. So this is equivalent to, so this was equivalent to 2 plus 2 upon 1 plus root x is less than epsilon, and which was equivalent to showing this. Hence we have shown existence of k greater than 0 such that x greater than k implies root x minus x upon root x plus 1 is less than epsilon. Hence, by definition of limit at infinity, limit x tends to infinity, root x minus x upon root x plus x is equal to minus 1. So this we have shown. So this proves question number 5. So in this video I will solve only question number 5 because it has many parts. In the next video I will solve from question number 6 onwards, and we will see how many questions we can do in the next part. Till then, stay tuned and subscribe to our YouTube channel for further updates. Thank you.